listen up. So we're talking about forces. I've got an object. Let's say I've got this cue ball, okay? I've got a ball sitting on the ground, okay? It's just sitting there. Is it going to move? It's sitting on my table. What's it going to do? Is it going to move?
No.
What's going to make it move? What's going to make it move? I have to apply a force. I've got to put some sort of force, okay? To make that thing move, right?
It's like crochet.
Crochet or a hammer or something, okay? It's croquet, okay. So it's going to go, there's got to be some sort of force applied to that ball to make it move, okay? Then, once the ball is moving, okay, that was the force of gravity right there, yep. Once I've got the ball, oops, a hard time drawing when I'm standing up. Once I've got the ball moving, okay, oops. Once I've got the ball moving through the air, let's assume that there is no gravity for the moment, okay? Assume we're in space. This is the the moon, okay? All right, little alien dude. Okay, this is a gravityless moon, okay? Zero gravity, zero mass, right there. So the ball is flying through the air, okay? It's flying through the air. And there's nothing there, and there's no rocket engine, no nothing. Is there a force being applied to it?
Air resistance. No.
There's no air.
You just said no.
Through the air resistance is air. In space. Through space. It's flying through space. Sorry. There's no air. Okay, it's flying through space. So, is there a force acting on this? No. There is no force on this ball, right? So what's the kind of motion that it has? Constant what? Constant velocity. Okay? Constant velocity. What's going to make it change velocity? Some other force. Okay? It's got to be a force. It's got to be an alien ship that's going to going to actually blast it and make it move. Okay? Now, here's the question I have. Here's the question I have for you guys. Okay? If my ball is moving at a velocity of 5 meters per second at an angle of 0 degrees, okay? Then I have my force, my alien laser beam, okay? And it then changes it changes the motion of the ball so that it's still going with a velocity of 5 meters a second, but this time the angle is 30 degrees negative. Okay? Did my velocity change?
No.
What is
Yes,
velocity?
it did change.
Why did it change?
Yes, it did change.
Okay, because I'm going in a different what? Direction. What is a velocity? What are the two things that velocity is made up of?
Speed and direction.
Speed and direction. If I change we have for the most part we've been talking about just magnitude changes. Okay, but if I change the direction of my ball, I'm also giving it. In order to change. And by the way, how did it change directions? It's okay. How did it change?
Purple.
I'm all tied up. Stop.
Is that you think it will go down the recording?
Yeah, it will. Oh no, it won't. All right. Okay. So here's the deal.
Oh,
Okay.
back there.
All right. So I'm changing directions. If I'm changing directions, I'm also changing velocity. So my velocity, I have a change in velocity. If I have a change in velocity and I do it in a certain amount of time, what do I have?
Acceleration.
I have an acceleration. Okay? And because we know that, does anyone remember Newton's second law? Okay. If I have an acceleration, that means I have to have a force. So in order to change the direction, even though I don't change the magnitude, I have to have a force. A great example is if I take my cue ball and I spin it around. I spin it around. Okay, so I'm spinning it around my head, right? Guys, I'm taking the ball and spinning it around my head. The velocity of the speed of the ball, the speed of the ball is what? Pretty constant, right? But what's changing? So there must be a what?
Force.
What's the force? Okay, centripetal. We'll deal with that later. But where's the force coming from? No, immediately to the ball. The string. The string is causing the ball to change directions. If I let go of the string, what's going to happen to the ball? It's going to fly off. Is it going to continue to be in a circle? No, it's going to go off in a direction. Okay, we'll deal with that specific stuff later when we get to centripetal force and centripetal acceleration. Okay, but you need to know that a force is required to change an object's direction, even if you aren't changing the magnitude. Okay, so Newton's first law is that an object at rest will stay at rest. An object with a velocity will stay at that velocity unless a force is acted upon it. Yeah. And when we talk about velocity, we're assuming Mr. Zeta, wake up. Your eyes are closed. When we talk about when we talk about velocity, we mean what two things? Magnitude, speed, and direction. So I could in order to change if that ball is staying at a velocity, that means that velocity has to change direction unless a force acts upon it. Does that make sense? Everyone so far clear on that point? Okay. Newton's second law, okay, talks about how the force, is proportional to the mass times the acceleration. So that means that my force is proportional to a mass times acceleration, or is equal to my mass times acceleration. Now, let me ask you a question. What does air above the A mean? It's a vector. That it's a vector. Is my mass a vector? No. Does it have a magnitude? No. Does my mass have a magnitude? Yeah. Yes. I have a certain amount of mass, right? Oh, yeah. Okay. But does it have a direction? No. So it's not a vector. But if my acceleration is a vector, what does that? If my force is equal to my mass times acceleration, what does it mean about my force? It's also a vector. And its direction, where does it get its direction from? The acceleration. Or vice versa. The acceleration direction comes from the direction of the force. Okay? Force, our mass, what's a unit for mass?
Grams.
Okay, in this case, we're going to use kilograms. Grams are, that's fine. Kilograms. What's a unit for acceleration? Okay. So, and the force, does anyone know the unit for force? Newtons. Okay. Now look, this is important. What this means, what this formula means. Now listen, I want you to understand the formula. Understand it, not just remember it. What this means is that it requires 1 Newton of force to take 1 kilogram. 1 kilogram. And do what with that 1 kilogram?
Change its direction.
Not just its direction, just its what? Its velocity. It's going to change its velocity. How is it going to change its velocity? 1 meter per second. Every second. Okay, so it means that it's going to take 1 Newton of force to take 1 kilogram of stuff and change its velocity by 1 meter per second every second. Now, does that mean I'm changing it positively or negatively? Do I know? Don't know. But whether it's a negative 1 meter a second or a positive 1 meter a second, it's a change in velocity. So it's going to take 1 Newton of force. What's the positive and negative all about? Direction. Positive, negative is about direction. Okay? So it's trying to take 1 Newton of force, take 1 kilogram of stuff, and accelerate it or change its velocity 1 meter per second every second. So if I were going to take 1 kilogram of mass and change its velocity by a half a meter a second in 2 seconds, how many newtons is it going to take? I'm going to take 1 kilogram of mass. I'm going to change its velocity by a half a meter a second every 2 seconds. 1/2. How many newtons is that? 1/2 a meter per second times 1 over 2 seconds, right? So that's going to be 1/4 of a newton. Right? It's just times 1 kilogram. Right? Everyone see that? Okay. We're not talking about direction, we're just talking about the amount of force. Okay. Let's do another very fast one. If I had 2 kilograms of mass, I'm going to accelerate it at 5 meters a second. Let's say I had 2 kilograms of mass. I'm going to accelerate it at 6 meters per second every 2 seconds. Okay? How much force am I going to be required to do that?
6.
Okay, 6 newtons, right? Okay. If I had a 2 Newton force and I acted on 2.5 kilograms, what's my change in velocity every second? It's what now? It's not 1.5. 2 over 2.5, right? 2 over 2.5, 2 over 2.5 meters per second squared. Okay? Is that cool? Everyone with me? Okay. All right. We'll deal more with that in a little bit. So we have Newton's. So Newton's second law is F equals ma. Newton's first law is, what's Newton's first law, guys? Let's get rid of the word motion. Let's say traveling at a velocity. Traveling at a specific velocity. Okay? We'll stay at that specific velocity unless a force is acted upon it. And why am I using the word velocity?
Get into our brains.
Well, that too. But to deal with making sure we understand magnitude and direction. Okay. We have Newton's third law. Does anyone know what Newton's third law is? Anyone know Newton's third law?
Reaction. I don't know.
Say it again.
Oh, yeah.
Go ahead.
Reaction has an opposite.
Okay. Let's do it. You've heard every action has equal and opposite reaction, right? Okay. So here's the deal. Alright? This ball is going to sit on the table. Okay? What forces are acting on this ball?
Gravity.
Gravity is acting on the ball. Is there another force acting on the ball?
Table.
Okay, why? What do you mean the table?
It's a push.
Pushing what direction?
It's pushing upwards.
Okay. How much force is the table pushing back on the ball?
Enough
It's
to-
the ball.
Enough to equal the ball, right? So here's the deal. Okay? Let me see the bowling balls in there.
Oh, it's a wind holder.
Okay. So this table, let's say, And there was a buddy of mine. You know what a thermos is? It's
Yes.
a brand name.
Yes.
It's like an insulated
It's a brand.
cup.
Yes.
And he says, thermos. It keeps the hot things hot, the cold things cold. How do it know? How do it know? Hot things hot, cold things cold. Now here's the deal. This table supports a half a newton. It now supports, pushes back 20 newtons. How does it know to push back 20 newtons?
It is.
Because like the design of the table, like
It's
if it was
not-
more, it wouldn't be.
But wait a minute, but it's changing its reaction force like it's alive.
Is it
It is
alive?
alive. Everything's alive.
That's the simplest thing.
Yeah, that is.
Let's touch.
You want both of them because it has a acne kind of. It's not like it's pushing upwards on it. It's kind of staying in place. I don't know.
Okay, Ellie is on the right path. I'm going to show you how it knows. As far as your pencil. Okay. This is like a tenth of a newton or something, right? The table's pushing back, right? Huh? How do it know? Okay. The ruler's pushing back how much?
1/10 of a newton.
The
Whatever the pencil is.
okay, we'll talk about this in a second. Talk about weight. This is weight and mass are different.
You call this.
Okay? Well, let's say, but weight is a force. Weight is a force. So we'll do that in 1 minute. But so the pencil on the ruler has a certain amount of weight. Not very much. Do you see the ruler doing anything?
No.
Yeah. The ruler's pushing back. Now, I'm going to put this cue ball on. Watch what happens. Do you guys see anything with the ruler?
Like
It does what? It bends a little bit. You see it?
Oh yeah,
It does, doesn't it? Okay?
Oh no.
Hold over
its like
Do it.
Now what do you see? Okay. On a microscopic level, the table's doing the exact same thing. The table is bending. There's a maximum amount of load it can handle, isn't it? And this ruler is getting pretty close. You can see because it's about to snap. Right? So, the way the material itself, this weight on the material is causing, the weight of the material is causing stress, internal stresses. The fibers, because this is wood, this ruler is wood, the fibers in the wood are being stretched apart. Okay? They're being stretched apart. Until at some point, they rip apart. And they snap. Now, break a rule. I did it last year and I immediately regretted going, oh, well, that was one that went down. Okay. I think Mr. Bryce is commandeered my
We could break that thing over there that you like to cut it.
Yes.
Yes!
Yes.
Yes! Slow down. Right. Let's slow down. Slow down. Behind you on the floor.
Yes.
Whoa!
It's already there.
Very thin and long. Thin and long like a roll sheet break.
Yeah.
So now look.
Yeah, it's not.
Oh man.
Yeah.
Alright, so now here's the
We
thing.
need to like.
Let me ask you, here's an engineering question. Here's an engineering question. Okay? Where is the weakest point on this board? Let's think about this. Where's the weakest point on this?
Probably
Right in the middle.
Where the holes are. Why where the holes are? There's less material. Okay? It's gonna break in the middle here. It's gonna break some more over here. Should. Call me a liar. Are you ready?
Oh,
you didn't like.
Oh,
It didn't even break.
you trying to break
Where did it break?
in the middle.
Right? Where is
You're not a woman.
Okay?
Let us break your word.
Okay. So the idea is that you can see how this stuff is stretching and cracking and moving. There's fluid here, there's plywood, so there's fibers, there's fluid, all sort of stretching and breaking. Till reaches maximum load, okay? So the idea, guys, is that even though I'm pushing back, so even though, so this floor here that's in the room, if I walk in, the floor's going to push back at 160 pounds.
Alright.
A lot. Okay? But if we're all here, it's going to push back all of the weight. The weight's going to push back and stretch, and the stretch is going to push back to account for all of our weights. The weights of the material, the tabletop, the walls, the weight of the roof pushing down on it. They have to calculate the structure and design of this floor so that we can withstand with a factor of safety without bending, right? Because you don't want to walk into the floor and all of a sudden the floor
How
bends.
does it hold it?
Okay. So they've got to design it to deal with those forces. Okay. Okay. Okay.
How much do you think the concrete in here weighs?
Well, that's the thing. The structure of the concrete has to be able to withstand the weight itself as well. It's a really mind-boggling, right? And because the concrete, it's not cement. It's not cement is the glue. Concrete is the cement plus the aggregate rock and stone and gravel and sand. And inside the concrete is rebar material. It's actually a composite. What we're standing on is a composite. It has the strength of the steel rebar, the steel bars in it, and the concrete itself. And together, we can do some really interesting things. Yes?
You know what's scary? Whenever bridges start swinging, shifting and stuff.
Yeah, but they're designed to do that. Most cases, yes.
That's scary.
Where's your pencil?
I don't want the bridges.
Oh, he's got it right here in front of you. Can you give her pencil back? Sorry. Okay, all right, listen up, guys. Okay. So when we talk about weight, let's talk about weight for a second, okay? Talk about weight for a second. I'm going to get to this last third law. We're talking about weight. The force, when we talk about weight, what's the force acting on someone to give you your weight?
Gravity.
Gravity, right? Gravity. So the force of gravity is equal to your mass, okay, times your mass, times the acceleration rate of what? Gravity, okay? So does your mass ever change if you're here or on the moon? No, but what changes? Your weight, because what is changing? The acceleration rate due to gravity, right? So your acceleration rate due to gravity is changing, and therefore your weight is changing. So the force, so if I'm 160 pounds, which I'm not, if I was 160 pounds here, and I'm on the moon, I'm going to be even less, okay? So because the acceleration rate's less, because the moon has less mass. All right? Okay. And we'll get into some of that, hopefully, if we can get into some orbital stuff. I don't think we'll do that this year, but we'll see if we have time. But I want you to be sure when we talk about weight, weight is the force due to gravity. Okay? So when we talk about that ball, that bowling ball, okay, and it's sitting on top of a table, or sitting on top of the ruler, say, right? We just had. Oops, that was really horrible. Okay, so there's the bowling ball sitting on top of the ruler. It's causing the ruler to do what? To bend, right? It's causing it to bend. So when I look at this bowling ball, I can do what's called, I can set up and talk about the forces. And what kind of forces do we have on the bowling ball? Well, the gravity which is pulling down. Notice I'm using an arrow. The force due to gravity. What does that arrow mean? Let's take it. Yeah, there's another V word I'm looking for. With a V.
Vector.
The vector. This is the vector. Remember, when we draw vectors, guys, when we draw vectors, we have it's an arrow with a magnitude and a direction, right? There's a magnitude of that vector, right? Everyone with me? Okay. What's the other force acting on the bowling ball? The ruler, so it's doing what? It's pushing up the force of the ruler. Okay? So now, what was the acceleration rate of the ball? With the bowling ball sitting on the ruler, what's the acceleration rate of the ball? When sitting on the ball? Okay. When we talk about forces, we need to understand the net force. The net force is the sum of all the forces acting on the object or the body. In this case, it's equal to what? Okay, it's equal to 0, but what are my two forces? Fg plus F of the ruler, right? Okay, Fg plus F of the ruler. Now, Fg happens to be in what direction? Negative. And Fr happens to be what? Up. So it's negative and positive, and they are the same value, right? They have to be the same value in order to equal 0. If they weren't, what would be happening to the ball? I'm sorry? What kind of movement? What kind of movement? Let's think about this. If, let's say my force net, which is equal to my Fg plus my Fr, was not equal to 0. My force net, that force net is really equal to the total mass times the net acceleration. Is my mass ever equal 0? In a case where I have an object? No. So if it's not 0, what can accelerate? What does acceleration have to be? If my force net does not equal 0, what does my acceleration have to be? Has to be anything but 0. Do you follow me? In order for this equation to be, if my mass is non-zero, in order for the sum to be this multiplication to be non-zero, my acceleration has to be non-zero, which means I'm doing what? If my acceleration is non-zero, it's some number. What kind of motion do I have on the object? Constant acceleration. Now, do we know how much of that acceleration is? Not until we put the numbers in. But there's a constant acceleration. Do you guys see that? Now, the ruler and bowling ball is kind of maybe throwing you for a loop because you're saying, look, if the ruler isn't putting enough force on it, then it's broken and it's going to be falling at gravity's rate. You're right, okay? But let's think of it this way. I'm going to move this guy off to the side. All right? And let's think about another option. Let's say I have an object that is being, let's say I have a rocket. Okay. All right. And it's pushing with a certain amount of thrust or force. So the engine is pushing on the rocket with a certain amount of force rocket. Okay? So it's trying to accelerate this, right, at a certain rate. And that force of the rocket is my mass of the rocket times the acceleration rate of the rocket. But if I have a big funky sponge here, okay, I know, a big sponge, and it's in front of the rocket. What's it going to do to the rocket? Slow it down. So it's applying a force what way? Applying another force, the force of the sponge, in that direction. But let's say the force of the sponge isn't strong enough to stop the rocket, it's just strong enough to slow it down. That means my force of the rocket plus the force of the sponge must not equal 0. Which means that that means that whatever value this is, whatever number this is, my force net must equal my mass times my acceleration net. Does everyone understand that? Everyone understand the term net? Net meaning it's all my positives plus my negatives, right? Everyone with me? Okay. So This is important because what we're going to do is we're going to be doing these things called free body diagrams. So I have some object that's represented like a square. You can represent in whatever form you want. We're going to create what's called a free body diagram. FBD. Okay? So if this object is in space, or let's say it's in the air, okay, but we're on Earth. So what's the first force that's applied to it? Gravity. And that is acting down, F of G. But let's say it's this object. Let's say what we're going to be doing is we're going to be modeling a book. Okay. Hold on a second. And we're modeling that book on a table. Okay. All right. So this is going to be a model of the book on the table. Okay. Where it is, we're looking, guys. We're looking at this book from the side. Okay, so our force of gravity is pulling down. What's the other force acting on this? The table. What direction is it pushing? Up. So force table. So I can draw that free body diagram with the two force vectors. Two force vectors. One pushing up, one's pushing down. You'll notice that the vectors are the same length. Why are they the same length? Because the force net is 0 because the book isn't falling to the table. Therefore, my magnitude, which is the length of the arrow, has to be the same. Now, because they're vectors, remember how we talk about having a velocity vector and we have the Vx and the Vy? Remember this? From like 2 days ago, right? And we solve this problem by doing the velocity V, and we say, here's my Vx, and we move the velocity y vector over to here, don't we? Right? So we get our triangle. What I've done is I've taken this velocity vector, okay, I've taken this velocity vector, and all I've done is I just moved it. Vectors can be moved anywhere as long as you don't change the direction and the magnitude. Does that make sense? So that means that I could take this table force and I could put it up here.
Oh, you took a little bit of the line.
I know. Uh-oh. But do you see my point? Okay. I could also do this. I could also take this and put this here. Like this. And I can do this. And I can put this up here. Okay. Can do either of those. Okay. So you can move them around. You can put all of them up here. It really doesn't matter. As long as you're getting the direction correct, the direction location. Now, could I do this?
No.
Because the force of the table is pushing to the side? No. All right.
That's a different direction.
That's weird. Oh yeah, that doesn't make sense.
Okay. So the idea is that when we talk about our problem solving, okay, and we talk about drawing a picture, this is the first picture you're gonna create, is your free body diagram. You're gonna create a model or picture, and you're gonna create this free body diagram to represent everything that's going on in your model, F of G, F of T. Okay? Here's the beauty, and I think was I talking to you about everything equals 0? I was talking to you about, yeah. Here's the magic of all physics and all engineering. Okay? This is the solution. Listen, you want the secret to life?
Yes.
This is the secret to physics. Okay? Okay? This is all you ever have to know. And if you know this, you can solve any physics problem you want. The sum of anything equals 0. Sum of everything equals 0. The sum of your forces equals 0. The sum of your torques equals 0. The sum of your energy equals 0. Okay?
Wait, Mr. Gray, you said, what did you say?
So every answer on the test is 0.
No.
Wait, you said if you know this, you know all of physics.
You know all of physics. That's all of physics right there. Nothing can be destroyed or created. You can solve every problem by understanding that it all has to add up to zero. Okay? If we're talking about, a lot of the things are about equilibrium. Because if it's not an equilibrium, there's something left over to get back to equilibrium, isn't there?
Yeah.
And if you figure that out, you can figure out where you are. So it's all about this. When we talk about energy transfer, heat transfer, if I talk about heat, I gotta have the heat's gotta go somewhere. And it's either gonna go, if I'm heating up a stove, the heat's gonna go into the pan, into the food, into the air, into light, into sound. It all goes somewhere. You just have to account for it. So all of that heat, all of it adds up to zero, because the heat going in must equal the heat going out. Okay? Does this make sense? What's our time frame? Got a minute? A minute? Okay, does this make sense? Okay, we're gonna start doing some more of this stuff. We're gonna make force and vectors. Have a good weekend. But guys,